What's that? Uh-huh. Always early birds over here. Probably bored today. I don't know if this one is good. It's a busy room today.
Yeah, good crowd today.
I think you scared them all away.
Too much math last time.
Too much.
All right, it's 4 o'clock, so let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, doing good. Yeah. We're end of week 11, and so things are wrapping up this semester. And so the midterm project is out there, and so I know you guys have been working on it. So I've gotten quite a few questions. I got a couple emails in my inbox, I think, over the last couple hours. I haven't had a chance to answer them yet, just because I've been working on other stuff. But I'll try to get back to you after the class today. Okay. So definitely, get started on your project. I think what a lot of people are seeing is that the image data that you have for your projects they're a little bit harder to work with than the tutorial, right? So there's a reason that the tutorial was the tutorial, because it's a little bit easier to work with than than other data sets. And so if you haven't had a chance to start your project yet, I would definitely go ahead and do so. I think the thing that's been most difficult for people is just finding where to get started. And so if you if you're having trouble with that, please just shoot me an email and I can get you going on where to find the first blood vessel list. Okay. All right, and so that's it for my announcements. And so are there any questions I can answer before we get started?
Extra credit for those in person?
No, unfortunately not. Yeah, I know we've been doing a lot of math recently, and a lot of this stuff is so this class is interesting because the material for this class is actually really designed for like a graduate level course. Because it is the stuff we're covering is very advanced, and so we're doing very advanced fluid mechanics, very advanced kind of PDE stuff, and I've thought long and hard about how I can teach this to undergraduates at a level that has less math, and it's hard, and I'm still kind of working my way through it as we kind of speak. So, but I will say this, that a lot of the really heavy mathematical derivations that we're going through, what I want you guys to get out of this is not really the details of the math, because this is probably the first time you guys have solved the PDE before. What I want you guys to get out of it is kind of more the higher level kind of conclusions from that. Like when we arrive finally at an equation and we talk about the general characteristics of that equation, what this term means, how this affects our flows and pressures. That's the part that I really want to get at. And unfortunately, it's hard to kind of talk about those things without going through the whole derivation, and that's kind of why I do them. But for your final project, you're not going to be doing these calculations for the final project. I know everyone's thinking about the midterm exam that's going to be in about 4 weeks. The midterm exam is going to be reasonable, and so usually my policy for my class is that anything that if I don't ask you to do it on the homework, then I'm not going to ask you to do it on the exam. So I think that's unfair, right? If I'm going to ask you to do it in a very time constrained setting, I'm going to ask you to do it in a homework first, just so that you guys get the practice. Okay. And so if you look at the past 3 homework assignments that we've done, that's kind of the level that I would expect you to do on the exam. So a lot of the like this part of the class is really heavy on the mathematical derivations. I want you to kind of, I want you to pay attention, of course. I want you to listen, but try to kind of pick out the higher level details more so than just kind of the lower level, like technical, in the weeds kind of mathematical stuff. Okay. And so today I want to get at some of that. And so today we're going to talk about, what do all those calculations mean? And that's what I really want you to take from these lectures and take them to like an exam, or, and, of course, take them outside the class so you can, demonstrate your understanding of this. Okay. But without having previously taken a course in like partial differential equations, or without previously taking an advanced fluids class, I know a lot of this can be kind of a lot, but and so when we're going through these mathematical derivations, just kind of focus on what's kind of the bigger picture, in terms of all that stuff. Okay. And so with that said, let's dive back in. Let's dive back into the math. Okay. We have just a little bit more to go, and so there wasn't too much more of the derivation left. And so we're going to pick up right where we left off, talking about impedance and vascular networks. Okay. And I want to start by talking about some of these terms that we kind of covered near the end of the course, right? Or near the end of the class. And these are kind of the 3 definitions of impedance that I really want you guys to focus on. Right? Right, so the first one is terminal impedance, and so that has the symbol Z sub T. Okay. The terminal impedance represents all the impediments or all the resistance to flow downstream of the vessel that we're considering. Okay. And so if I draw a characteristic blood vessel like this, okay, and so we'll say that the blood is flowing inside this blood vessel. Okay. Okay. Once the blood leaves this blood vessel, it's going to face some resistance to its flow, because we all know that blood doesn't flow freely. There's always some resistance to it, right? And so for all the vessels that are downstream of this, and so let me just kind of represent them as just kind of like this fractal tree, right? All of these guys are going to have some resistance, right? And that resistance is going to be felt right here at the outlet of this vessel. Okay. Think about it. Think about the analogy of, you're driving your car on the freeway, right? So let's say you're driving on the 57. Okay, you're just pulling out of on Nutwood from Cal State Fullerton. You want to go home, but 5 miles down the road, there's a big pileup and a big crash, right? And so even though you're 5 miles away from that crash, you still feel the effects of that resistance, right? And so fluid mechanics and traffic actually share a lot of similarities. And so if you and so I always say, for people living in Southern California, I think you understand fluid mechanics a lot better than you think, because you drive on the freeways around here, and everyone here knows what traffic feels like. And so even though we have impedances, and even though we have resistances in the downstream vessels, that's still felt upstream on the tree, because all the fluid there is connected. Right? Okay. And so we can encapsulate that effect into a single term, and we call that terminal impedance, Z sub T. Okay. Yep. Mm-hmm.
So are you saying that the slowdown is happening where all the segments are?
Yes.
Like you can feel it at the beginning of that too.
Exactly.
Well. Okay.
Yeah. Yeah. Mm-hmm.
So it's not just felt at the separation.
Exactly.
Okay.
Right. Right. And so things propagate in fluid mechanics, right? And so you affect something downstream, but that affects stuff upstream as well. All right. But with that said, just like you can have resistances downstream, this vessel itself also causes some resistance to flow as well. Okay. And so the fact that each individual vessel can cause impedance to flow, we call this the characteristic impedance. Okay. And we give that the symbol Z sub O. And so we can define that here. So we call that characteristic impedance. Characteristic impedance is the impedance or the resistance that comes from a single vessel. Okay. So those two definitions are kind of core. They're kind of central to how we're going to proceed with the calculations. Okay. And so terminal impedance, you can almost think of it as like a collective impedance for everything that's downstream. Okay. And the characteristic impedance is the impedance for just a single vessel. Right? So one way you can think about this is that I've kind of drawn a network of vessels at the end right here. One way that you can look at is that each of these vessels have their own characteristic impedance, right? Because each of these individual vessels will apply some kind of impedance or some kind of resistance to the flow. Right? So anytime you look at a single vessel by itself, that is going to have some characteristic impedance, right? And so one way that you can think of the terminal impedance is that the terminal impedance is kind of the collective effect of all the characteristic impedances downstream of that vessel. Okay. Okay. All right. So I want to draw a picture of what this kind of looks like in a network, because these definitions can kind of slide depending on which areas of the network that you're looking at. Okay, so let me draw kind of a relatively simple tree. So let's say that we have one vessel coming in, it's going to branch off, and these two are going to branch off. Okay. So this is a trifurcation. Okay. So let's say that we have a, this looks like a maple leaf, but it's a network of blood vessels, right? Okay. And so we start with one parent vessel, and that's going to split off, and then each of those daughter vessels are going to split off as well. Okay. This is pretty condensed, and so normally you don't have this much branching off in such a short area or short space, unless you're looking at like a pulmonary artery or something like that. But I think it's good for this example. Okay. All right. And so let's say that we want to focus on this particular vessel right here. Right? So we want to look at the parent vessel, right? Okay. This parent vessel is going to have its own characteristic impedance, right? Because it's a single vessel. Okay. Right. And so one way that you can interpret this is as the blood flows through that parent vessel, or in other words, as it goes from the front end and it flows to the back end, right? The amount of impedance or the amount of resistance to flow that it experiences can be captured by Z naught. Okay. All right. And so that's what happens from there. Once the blood leaves this parent vessel, it's going to enter the network of vessels that come after that. Right? Okay. And of course, as the blood leaves that parent vessel, it's going to it's going to experience an impedance to flow that is a result of all of these other vessels here. Okay. And so what we can say is that instead of doing all of these calculations here, which have all of these vessels, what we can do instead is, if we know the collective impedance of all these vessels, we can instead do this, where we just model a single vessel. Okay. Instead, we're going to represent it as a single vessel, where the single vessel still has Z naught. Okay. But the collective effect, or the collective impedances for everything downstream, we summarize that as Z sub T. Okay. Okay. And so from a computational perspective, this saves us a lot of work. And so instead of solving, let's say that we want to solve the 1D equations, right? And so instead of solving the 1D equations for this huge network of vessels, right? And so we're gonna have to do it for, I don't even know how many vessels there is here. Maybe there's like 12, 13. Okay. And we can instead do it for one, but but what we can do instead of all the 11 or 12 downstream vessels, we just represent that by its terminal impedance. Okay. Yeah.
I know we talked about it, but I'm kind of forgetting. If you look at the top segmentation of that vessel system right there.
Yeah.
So you have a parent, it splits off into the first daughter vessel right there.
Yeah. Mm-hmm.
Does that daughter vessel go from like start to the very end, or is that daughter vessel branch off into 3 separate new vessels?
Yeah. And so I mean, for the sake of the projects, this would be like, this would be one vessel here, and this would be number 2, and this would be number 3. And so, in terms of like vessels that you would model, that's how you would classify it. But for the medical classification, they actually classify vessels in terms of size. And so if you look at a situation like this in practice, they would probably consider this as a single vessel right here, right? And then after it splits off into 3, what's likely going to happen is that the vessels are going to shrink because of Murray's law, right? And so it would consider this one as a separate vessel, this one is a separate one, this one is a separate one, because all 3 of those would probably be around the same size in terms of radius. And then once it splits off again, these two would be classified itself as well.
If you were to name those in like the professional world, would you be like daughter 1, daughter 2, daughter 3?
You would probably classify them. So there's a class specification. So I think it's called like class 0. And so the biggest vessels would be like class 0. And class 0 has a size range. And so it's anywhere between maybe like 3 or 4 centimeters in diameter. And then you go down, that'd be a class 1 would be like 1.5 to 2 centimeters, something like that. But informally, you know, people say like daughter 1, daughter 2, just because it's kind of easier in the moment to say. All right. Okay, so that's you know, kind of one way that we can use these ideas of impedance to kind of, you know, simplify our work. But this also goes in other strokes as well. So let me go ahead and kind of erase those circles. I'm gonna use some different colors here. And so let's say instead that we're interested in this vessel right here. Okay. And so this vessel, of course, has its own characteristic impedance. Right? Okay. And of course, these vessels are going to split off into two more, right? And so just like we did with the parent vessel here, and we said that all of those, all of the collective vessels downstream will have a terminal impedance. We can also, by the same token, say that these two vessels will create a terminal impedance for this vessel right here, okay? And so what you interpret as terminal impedance and characteristic impedance, it really depends on which vessel that you're kind of focusing in on. And so, you know, when you're looking at a big kind of network like this, it's always good to kind of focus on just one particular vessel at a time and say, okay, what's everything downstream of this? Then let me just characterize that as the terminal impedance. And then the vessel itself that I'm looking at, then that has a characteristic impedance. Okay. And so, you know, what you consider terminal and characteristic, you know, it really just depends on which vessel itself that you're looking at. Okay. And so if you think of it from the perspective, you know, focusing on one vessel at a time, then you look kind of relative to that, you know, what's downstream of this, you know, what's this vessel, and, you know, then the definitions become a bit more clear. All right. Any questions on this? Okay. All right, so let's introduce another definition, but this one's interesting, I think. Okay. And so let's talk about pressure wave reflection. Okay. And the way that we're going to characterize reflection is through this thing called the reflection coefficient. And so I had to kind of talk about terminal impedance, characteristic impedance, because it's important to discuss for this reflection. Right? And so to introduce this, you know, let's kind of remind ourselves that when pressure waves travel along the cardiovascular system, you know, we expect them to kind of travel and reflect. Right? Okay. Remember our example where we did a string attached to a wall, right? And so we know that when we pulse a string, right? And so when we kind of like, you know, think of this as a guitar string, say we strum the guitar, then there's a wave that travels along the string. Right? And then eventually when the pulse reaches the wall, right, it's going to reflect on the wall and come back. Okay? Maybe it comes back with the opposite side. That's kind of the simplest kind of example of wave reflection. But in this case, you know, it's not it's not perfectly descriptive of what happens in the cardiovascular system because the reflection only occurs at one point. Okay. Okay. It's not until the pressure wave kind of reaches the very end of its path that it starts to reflect and come back. Okay. If you remember when we started this discussion of impedance, I told you that pressure wave reflection can occur at other locations in the tree as well. Okay. Okay. It may not be a full reflection, and a lot of times it's just a tiny amount of reflection, but these small reflections do occur. And the way that we can characterize that is in terms of characteristic impedance and terminal impedance. Okay? And so we have this variable here, and so we call it gamma. Right? Sometimes I call the symbol hangman. Okay, and this symbol right here, this is our reflection coefficient. And so it's a number, so it's a coefficient, and it can be anywhere between 0 and 1, okay? And so if gamma here is equal to 0, then that means we have no reflection. Right? And so if we have a gamma is equal to 0 in a situation, that means the wave just passes right on through. So there's no reflection, it just passes through without problems. Okay? The other extreme for this is when gamma is equal to 1, and this is when we have complete reflection. Okay. And so complete reflection is characterized as when the pressure wave reaches a certain point and it bounces back with basically the exact same magnitude and intensity. Okay. And so gamma is equal to 1, that would be kind of what happens here. Okay. And so when our string hits the wall, then we have a complete reflection of the wave, and so we can say that that's when gamma is equal to 1. Okay. But when you're talking about the cardiovascular system, we can have gammas that range anywhere between 0 and 1. Okay? And the way we compute that is through our characteristic and terminal impedances. And so the formula for it is this. And so we have a gamma is equal to Z naught, the characteristic impedance of this particular vessel, minus the terminal impedance. Okay, and so that's the impedance at the end of the at the end of the vessel, divided by the sum of these two quantities. And so this tells us what this equation tells us is that wave reflection occurs whenever you go through a change of impedance. And so basically, in other words, whenever there's a difference between the characteristic impedance of this vessel and the terminal impedance of the downstream vessels, that's when you get wave reflection. Okay. And so this most commonly occurs at the bifurcations, because that's when you kind of see a big drastic change in impedances. Okay? And so when you have a bifurcation, right, the vessel is going to split off into two. Oftentimes your two daughter vessels are going to be of different size, okay? And so because they're a different size, they're going to have a different impedance. Okay? And so if we characterize these with ZT, we characterize this with ZO, okay? You compute its reflection coefficient, and if there's a difference between the two, and likely there will be, then you're going to have some degree of wave reflection. Okay, it may not be that big a difference, you know, especially if the daughter vessels are kind of close in size to the parent vessel, you know, but there is going to be some degree of reflection. So what's going to happen is that if you have a pressure wave coming in, and so, you know, let's say the heart pumped, and as the heart pumped, that's going to create a pressure wave down your blood vessels. Okay, the pressure wave is going to come in. Some of that pressure wave is going to come back. And so, you know, we're going to have partial reflection here. Okay. Usually for something like this, the gammas are relatively modest. So they might be around like 0.1 or something like that. And so what that says, about 10% of the wave is going to reflect back. Okay. While the rest of the 90% of the wave is going to continue on. Okay. And so you can think of the reflection coefficient as kind of expressing what percentage of the wave bounces back and continues on. Yeah.
When it reflects, does it reflect completely the opposite way, or does it partially and then it goes back again?
So you can think of it as kind of like a portion of the pulse. And so if we have like a pulse that's coming in like this, and so let's say the pulse, just for the sake of simplicity, this has a height of like 1, right? And so when I say partial reflection, you know, I'll say we have a partial reflection of 10%. Then what comes back might be a pressure wave, and you know, this height might be like 0.1. But then what continues on is a pressure wave where this is 0.9. And so you can think of it as like an energy budget kind of thing. All right. And so, you know, whenever you have this change of impedance, then you're going to have some degree of reflection. Oftentimes it's very small up until you reach the very ends of the tree, but it's there. And if you think about how many times your blood vessels bifurcate in your body, you know, it's you know, it's a pretty complex phenomenon. Okay, any questions on this? Yeah.
Does it reflect more than once in a vessel?
Oh, absolutely. Yes. Yeah. And so what can happen sometimes is, you know, if we come up to an example up here, right? And so if you have a pressure wave coming in, and so let's say that you have a pressure wave coming in this way, right? And so, you know, if you have a bifurcation right here, some of that wave is going to bounce back. But then when it bounces back, you again kind of reach a bifurcation. And so you have also partial reflection that comes back right here too. And so, you know, and if you account for the fact that your heart is kind of pumping every single second, like about once per second for most people, then you have kind of pressure waves that are constantly going down, reflection coming back, and things like that. And so it's, you know, when you think about it, when you characterize it in terms of single pulses, I think it's not that hard to understand. But when you think about it in terms of how many pulses get sent down, how much reflection there is, you know, it's chaotic. There's kind of a lot going on.
That's what explains the resistance.
Partially, yes. Yeah. And so that's a part of the resistance as well. All right, question. So what would be the effects of the reflections? Yeah. And so, you know, for a lot of these bifurcations, you know, when the reflections are very small, I think even 0.1 might be a little bit high for these reflections. A lot of times they're only like 0.03 or 0.01, right? So we only have like 1 or 2% of the reflections going on. And so when these pressure waves get reflected, you know, they have some effect on the flow, right? And so, you know, that's kind of why we're talking about impedance now instead of resistance. And so when these pressure waves reflect, right? Normally you would expect the pressure waves to go down, you know, if this were a string, right? So the pressure waves would go completely down the string, completely down the length, right? Kind of alongside the flow. But when the pressure waves reflect, right? Then what's going to happen is that the flow that's coming next, and so the flow in the next pulse, is going to feel that reflected wave. think this is a bit easier. And so the flow that's coming in here, right? This flow is going to be impeded by this pressure wave that reflects back. And that adds to the amount of resistance that the blood vessel or that the blood flow feels, right? And so it's a lot more than just viscous friction. And so, you know, the flow is also fighting against these pressure waves that are kind of reflecting back. And so that's kind of the fluid mechanical effect on this, but there's also effects on how the vessel wall itself behaves. And so we're not really going to get into that a lot of this class, but you know, these vessel walls, you know, if you think of them as like a structure, right? Those vessel walls are going to be feeling these pressure reflections as well. And so that's going to affect things like the stress, the structural stresses in these walls. That's going to affect their, you know, how the cells respond on these walls. And so it's complex. And so there's really a lot going on. And so, you know, relatively speaking, I think we've made a lot of advancements in terms of understanding what's going on inside the human body. But you know, I'd say we're still kind of only scratching the surface, because you know, in terms of the physics going on, it's very, very, very complex. Yeah.
One quick question with that as well.
Yep.
I was just thinking about it. I might be wrong here, but if it's not stopping, but it's reflecting back, it has the ability to move backwards. That would mean that it has to have a greater force going back and going forward if it's able to push back.
Yep.
So how is there a greater force going back if it's just reflection of force going forward?
Yeah. So then of course there's another pressure wave going forward from the next pulse as well. And so once those meet, you know, they're going to kind of react as well.
So amplify and give it greater force going back.
It depends. And so if the waves are kind of in the same phase, then they would amplify each other. But if they're opposite phase, then they would kind of destruct as well.
Okay. If they destruct, then there wouldn't be any reflection. It would just be stuck there. Or?
Yes. And so if their magnitudes were exactly the same, then yeah, then they would perfectly cancel out like that. But you know, keep in mind there's tons of these kind of pulses traveling forwards and more reflecting back. And so there's tons of very kind of really complex interactions in these vessels. Yeah. So we're kind of analyzing it, you know, and I know we've kind of done a lot of really complex analysis here, but you know, we're still kind of only just kind of scratching the surface of you know, what these are. And that's why, you know, this class, you know, it seems like it's very niche. And so, you know, we're doing CFD and we're using it on a very niche subject. But, you know, that's kind of why there's such intense interest in using CFD, because there's so much physics going on that's kind of really impossible to kind of do it all by hand. Yeah, great questions, guys. Any other questions on this? Okay. All right. So let's see, where do we go from here? Okay, so that's the reflection coefficient. And so let's go ahead and bring this back to our solution, right? And so if you recall from last class, you know, we started this whole kind of journey with the 1D equations, right? And ultimately what we wanted to solve for expressions for the pressure and flow inside these vessels, accounting for this impedance. Okay. In other words, you know, we want an expression for Q of Z and P of Z, okay? Right. And so as a function of the centerline coordinate in the vessel, we wanted to find out how the flow varies and how the pressure varies that accounts for these impedances. Okay? And from the last class, we kind of stopped in the middle of solving of applying boundary conditions to these, right? Because one conclusion that we reached yesterday, the last class, was we solved for their general solutions, right? And so eventually we kind of massaged that that PDE system until we could get to an ordinary differential equation, and then we solved the ordinary differential equation, and we got solutions in terms of two arbitrary constants, right? C1 and C2. And so we were right in the middle of applying boundary conditions to solve for their specific solution. Okay? Okay. And so we weren't quite done with that, but I do kind of want to move on to the next step. And so, let's assume that we've done all the mathematical boot camp, and we plugged in our boundary conditions. Okay, and so we end up with the following. And so Q of Z is equal to Q naught, okay, divided by 1 plus gamma. Here you see our reflection coefficient, and so the reflection coefficient, it was, we kind of introduced it in terms of its physical definition, but it had a mathematical motivation as well to kind of simplify our answers. So we have 1 plus gamma times e to the minus 2 lambda L, okay. And this is multiplied by e to the minus lambda Z plus gamma e to the lambda Z minus 2L. Okay. So that's Q naught of Z, or Q of Z. P of Z is going to be Z naught, Q naught. Right? Remember, Z naught is our characteristic impedance, and so that's the impedance of the vessel that we're looking at. Our denominator is the same, and so we have 1 plus gamma e to the minus 2 lambda L. Okay. And then in the parentheses here, we have the same thing as well. So we have e to the minus lambda Z plus, or excuse me, minus lambda e to the lambda Z minus 2L. And so those are our expressions that that we can use to compute the flow and the pressure. Of course, these are not, I wouldn't call these practical equations. So these are not equations that you could solve by hand, but they do make great equations that you can plug into the computer. And so, the idea with these algorithms, and kind of is kind of an overall theme in this class, we develop not necessarily methods that you can do to compute by hand, but you set up an algorithm that a computer can do for you. So you write a code in MATLAB to do this, or you write a code in C++, Fortran, whatever to do. Okay? And so this is a good example of that, because these equations, it'd be really hard to kind of compute these by hand, especially when you have so many derived variables here. So we have gamma, we have lambda, the characteristic impedance, and so all of these are quite complex. And so it's a lot easier to set this up in code than anything else. Okay. And so with that, I want to define one more parameter here. And so we've already been introduced to terminal impedance and characteristic impedance. And so there's one more that we want to compute here, and that's called the input impedance. Okay. And so the input impedance, this is you can think of this as the total amount of impedance that you experience when you flow through a single vessel and all of the downstream vessels. Okay? And so one way that you can see it or one way that you can define it is as the impedance to flow as seen from the inlet as seen from the inlet of a vessel, okay? And so this input impedance kind of includes everything. So this includes the characteristic impedance, of the vessel of interest, okay, as well as all the terminal impedance as well. Okay, so let me go ahead and draw that out for you. So if we have our vessel right here, okay. Of course, this vessel is going to, have all of its downstream components. Okay. We've already seen that, all the downstream components, we call that impedance Z sub T, right? So that's the terminal impedance. The vessel itself has a characteristic impedance, we call that Z sub 0, okay? The input impedance, you can kind of think of it as just a combination of these two things, okay? And so the perspective is that if you're sitting right here, okay, so let's say that you're a blood vessel, right? Joe Schmo blood vessel, and you're, blood cell, right? Joe Schmo blood cell, and you're about to flow through this vessel and all of the downstream, right? What you're interested in is if you're standing here, and you're about to flow through all of these vessels here, how much impedance are you going to experience? Okay. And we call that input impedance, Z sub I. And so the way we define input impedance is, we utilize our solutions up there, okay? And so the input impedance is basically just the ratio of the pressure on this vessel and the flow, right? But we're going to define these at the inlet of the vessel, right? And so if we assume that, the vessel that we're interested in is this one right here, okay? What we say is that the coordinate or the location of this location is 0, okay? Right, and so we say that Z is equal to 0 there. And so we plug in 0. And if we plug in Z is equal to 0 in both of these expressions here, that's going to give us, the pressure at the inlet of the vessel and the flow at the beginning of the vessel, okay? And so if we plug in for that, what we get is Z naught 1 minus gamma e to the minus 2 lambda L divided by 1 plus lambda e to the minus 2 lambda L. Okay. And so we have 3 impedances now. And so we have the input impedance, we have the characteristic impedance, and the terminal impedance. Okay. Now that we kind of have an understanding of these, we can see, how they all combine together and how we can actually use these in some problems to do some computations. All right. Any questions on this? Okay. All right, so let's do an example. Let's do a simple example to kind of pull it all together. Okay. Okay, so let's do a simple bifurcation. So simple bifurcation, we have two vessels that look like that. Okay. We're going to assume that we know the terminal impedances of both the daughter vessels. Okay. And so we'll call this ZT1, and we'll call this ZT2, okay? And we're also going to assume we know the characteristic impedances of all three vessels as well, okay? And so we have Z0, we'll call this Z01, Z02, okay? And since this is the parent vessel, we'll call it Z0P, okay? Okay. All right. And so we know the terminal impedances, we know the characteristic impedances, right? And then remember the characteristic impedances, those are based on usually the physical properties of that vessel. So based on its size, based on its material properties, based on the viscosity of the flow in there as well. And so those are usually not too hard. So as long as you can measure the vessels and know how big they are, the characteristic impedances are not that hard to obtain. Okay. Okay. And so what we want to do in this situation, or what we want to compute, okay, what we want to compute here is the input impedance for the parent vessel. Okay. And so what we want to know is that if we're sitting at the input of this entire tree right here, or in case this bifurcation, what is the input impedance here? Okay. And so to do that, we're going to need to basically work our way from the back of the tree back up to the inlet. Okay. All right. And so we're going to use a lot of the formulas that we defined here to kind of work our way through. And I say compute as if we're going to get a number out of this, but what we're really designing here is an algorithm, right? And so because the formulas here are quite complex, they're kind of hard to kind of work with by hand. What we're going to do instead was we're going to basically design a recipe so that if we able to plug this into code, then the code kind of handle that for us. Okay. Any questions on this? Sure. So question is, can I explain how P of naught divided by Q of naught is the input impedance? Yeah. And so that kind of is based on the fact that the way that we define impedance is kind of this relationship between pressure and flow, right? That's ultimately what impedance is. And I think it's helpful to kind of think of it in this perspective. And so pressure, you can kind of almost think of that as like the forcing to your system, right? And so when your heart pumps, it's going to apply a force to the blood to force it through. And the way that manifests is through a pressure. Okay. Okay. Right. And so if you think of the pressure as like the force or the load that's being applied on the blood flow, right? Then the flow, that's kind of the response, right? right? So think about kind of a solid object, right? So in front of me right here, there's a roll of paper towel. And so I know that if I punch it, right, if I apply a force to that, then that paper towel is going to go flying across the room, right? And so the velocity at which the paper towel flies at, that's kind of its response, okay? And so pressure and flow kind of have that same kind of relationship in blood, okay? And so the ratio or the relationship between the amount of force that you apply and the resulting response, we describe that as impedance, okay? And so if the impedance is high, and so if you have a high amount of impedance, if you put a lot of force, then you're not really going to get a lot of flow, right? But if you have a low amount of impedance, if you apply, you know, a little bit of force, that's going to cause a big response. And so the impedance is kind of a ratio of, you know, how much work that you do compared to how much response that you get. Okay. Because the goal of the heart is to basically force blood through your entire system. And so, you know, the less impedance that you have, you know, the less the blood has to do. Okay. And the reason we apply it at 0 is because this is the input, and so we apply these guys at the input of our vessel. Question. So in my example, my impedance is the friction of the floor and the paper towel. Yeah, it could be like the air resistance too. You know, if someone is sitting right in front of me, you know, their face would also provide some impedance, right? Like if my goal was to punch the paper towel to the back of the room, you know, anyone's face would also provide resistance in doing it. Yeah. But yeah, friction, air resistance, that's probably the more general impedances that you can think of. Okay. All right. So how are we going to do this? And so how are we going to compute the input impedance to this network of vessels? Okay. And so the idea to do this is to kind of work your way back. So work your way to the front. So start from the back and then work your way up. Okay. All right. And so let's consider the two daughter vessels first, right? So for the two daughter vessels, we have both the characteristic impedance and the terminal impedance, right? Okay. And so since we have ZT and ZO, that means we can compute our reflection coefficient. Right? Okay. And so this is the first thing that you should compute. And so for daughter vessel 1, and so we'll have a gamma 1, okay? This is going to be equal to Z0 1 minus ZT 1 divided by Z0 1 plus ZT 1, okay? Gamma 2. And so this would be like Z0 2 minus ZT 2 divided by Z0 2 plus ZT 2. Okay. Okay. All right. And so that's significant because now that we have the reflection coefficients, if we kind of scroll back up and see what that allows us to compute, okay? If we look at this formula for the input impedance, right? All that it relies on here is that we have to know the reflection coefficient, we have to know the input impedance, as well as the length of the vessel, as well as lambda, but lambda is easy to compute, okay? And so from these reflection coefficients, we can use them to compute the input impedances of both the daughter vessels. Okay? So this will be, we'll say this is ZI1 is equal to ZO1 times 1 minus lambda 1 E to the minus 2 lambda 1 L1 divided by 1 plus lambda 1 E to the 2 lambda 1, or excuse me, minus 2 lambda 1 L1. Okay. And same for vessel 2. Okay. Right. And so now what we have is the input impedances for those two. And so, let me go ahead and draw our bifurcation again. Okay. And so what we have now is we have ZI1, ZI2, right? Remember, those represent the impedances of the vessels as if you were standing at the inlets. And so if you were standing at the inlet of this vessel, you would see ZI1. If you're standing at the inlet of this vessel, you'd see ZI2, right? And so we can go ahead and erase these vessels. And so now that we computed ZI1, ZI2, what we can say is that these will basically replace the impedance of those two vessels. So we can kind of eliminate them from the tree now, okay? And so in a way, we've kind of pruned them from the tree because we no longer need them because we've already computed what the total impedance is that you're going to experience when you flow down that vessel. Okay, and so we no longer need them. So we just have ZI1, ZI2. Okay. Okay. And so the two daughter vessels kind of represent the best case scenario of if you know the terminal impedance and if you know the characteristic impedance, you can basically use that to compute the input impedance. Okay. And so our two daughter vessels kind of represent that best case scenario. And so we're given terminal impedance, we're given its characteristic impedance, and so we can compute their input impedance. I won't say no problems because you have to kind of plug in a lot, but it is possible. Okay. And so if that were the case, if that were the case, the problem only really asks us to compute the input impedance of the parent vessel, right? And so we don't really care too much about the daughter vessels. It kind of seems like we don't, right? And so why didn't we just apply that same technique to just the parent vessel and just be done with it, right? The problem with that is that because the daughter vessels were in the way, we didn't know what the terminal impedance was of the parent vessel, right? And so until we can compute the terminal impedance of the parent vessel, we can't apply that same method to compute the input impedance of the parent one. Okay? And so our next objective here is to basically compute the terminal impedance of the parent vessel based on the input impedances of the daughters. Is there a question?
Yeah, I was gonna say, so when you apply like Murray's law to like find the terminal of the parent.
Yeah, you wouldn't be applying Murray's law. You would actually use. So we're going to assume that these two impedances are in parallel, and then we're going to assume they're basically parallel resistances, and so we're going to combine them in parallel. You'll see this. Okay. And so let's use these. And so we can use these two input impedances to compute the terminal impedance of the parent one. Okay. And so the ZT we're basically computing is right here. Okay. Okay. And so, let's recall the definition of terminal impedance. And so all terminal impedance is that's the impedances of all the downstream vessels, right? And so in this case, we only have two downstream vessels. We just have the downstream vessel for daughter vessel 1 and daughter vessel 2. Okay. And so with that in mind, then this tells us that the terminal impedance of the parent vessel is a combination of the two input impedances of the daughter. Okay. Okay. And the key word here is parallel combination, because once the blood kind of leaves the parent vessel, it can kind of go either way. Right? So it can go to daughter 1 and daughter 2. And so if you think about this from a circuit's point of view, when you combine two resistors that are in parallel, you have kind of the parallel resistor form for that. Okay. And so what we can say then is we can say that 1 divided by ZTP, okay, is equal to 1 divided by ZI1 plus 1 divided by ZI2. Okay. And so if we solve for this, okay, so if we solve for this, we have ZTP is equal to ZI1 multiplied by ZI2 divided by ZI1 plus ZI2. Okay. Okay. All right. And so let's go ahead and redraw our system. Okay. And so if we redraw a system now, we have a single vessel here, right? We know the characteristic impedance of the parent vessel, so we know that ZOP. Okay. And now we also know the terminal impedance of this parent vessel as well, because we just computed it, right? And so it's right there. And so now that we know terminal impedance, we know characteristic impedance, we can just follow the exact same steps that we did above to compute input impedance. Okay. And so first we're going to compute the reflection coefficient. Okay. And so we're going to have gamma P is equal to Z naught P minus ZT P divided by Z naught P plus ZT P, right? Okay. Then after we compute the reflection coefficient, we can then use it to finally compute the input impedance for the parent vessels. So we have ZIP is equal to ZOP times 1 minus gamma P e to the minus 2 lambda P LP divided by 1 plus gamma P e to the minus 2 lambda P LP. All right. So that's kind of the algorithm. And so, the algorithm is to kind of start from the backs of the tree. That's where you have the terminal impedances. Use those to compute the input impedances along the way until you finally reach the vessel that you're interested in. All right. Any questions on this?
Is that an equal sign?
It is an equal sign, yes. I know it's not satisfying when we don't get to plug in numbers, and so I know we're just setting up a bunch of equations. I know it's it's not the most satisfying thing, but these are all formulas that you would imagine you would plug into MATLAB, right? And so formulas for MATLAB is MATLAB loves formulas, and so you can imagine writing a MATLAB algorithm that kind of takes these, right? You plug those in, right? And you plug into this one, and then once you have that, then you do that. And so, even though this was an example, all we did was just set up a bunch of formulas, but those formulas kind of form the algorithm that you can use to solve these kinds of problems. Okay. And so one last thing that I want to talk about before we go is this example here is kind of sets up, like a general algorithm. Okay? And so what I want to do is kind of summarize all the steps that we did, so that you can apply this to a much bigger network of vessels. Okay. And so this is not that different from the example, but this kind of just summarizes everything. Okay. And so step one, you have to be given the terminal impedances for all the n vessels. Okay. Okay. You have to be given all those terminal impedances, and you have to be given the characteristic impedance of every other single vessel. Okay. Step two. Step two is compute reflection coefficients for all n vessels. Okay. Right, so that's what we did in the previous example. And then once you compute those reflection coefficients, you can use them to compute the input impedances for all the end vessels. Okay. Right. Right. So once you found the terminal impedances, or excuse me, the input impedances for all the daughter vessels, then you can combine them together to form the terminal impedance of all the parent vessels. Okay. Okay. And then once you know the terminal impedances of the parent vessels, then you just kind of repeat the process. And so, for the parent vessels, you can then compute its reflection coefficient. From its reflection coefficient, you can compute its input impedance. And from the input impedance, you can then combine that to form the terminal impedance of whatever comes next from the tree. Okay. And so this is kind of a recursive algorithm. And so, you basically, you kind of cycle up just like that. And you keep repeating this until you get the input impedance at the very beginning of the tree, which is often what you're most interested in. Okay. Any final questions on this before we wrap it up for the week? Okay, all right, and so we're done. We're done with that unit, and so we're done with impedance. Okay, thank goodness. Right, and so next week when we pick it up again, we're going to be talking about velocity profiles. So we're gonna kind of build off our Navier-Stokes results from before, and we're going to see what happens when our flow is unsteady. Okay, all right. So thank you everyone for tuning in this week. Make sure you guys are working on your projects. If you run into any issues, just don't be afraid to let me know. And I'll do my best to help you. And so hope you guys have a good weekend, and I'll see you guys next week. Thanks, guys. Bailey, did you have any other questions? Okay, all right. I'm gonna go to close up the call then. So I'll see you next week.